läks pihta. Okay, so let us start now recording and in English. And now there's a question of Raido was about the spectral flux. And so from spectral flux, you have different things. So right now my writing is a little bit not very good because I'm doing it on my laptop screen, so that so due to technical reasons, actually, maybe I just type in. It's like best if I type in spectral flux. And spectral flux, we can use it to derive something as follows. The first is Rachmaninoff's law. Then we have the Kolmogorov direct cascade, and inverse cascade, in which case we have actually two spectral fluxes. One is energy flux, and simultaneously entropy flux. And now, because of the interplay, you need to have inverse energy cascade. But in principle, you can think about other situations as well when you have spectral flux. For instance, you can also have a spectral flux of tracers. If you consider the spectral flux of tracers. Similarly, Rachmaninoff's law is based on the spectral flux of tracers. Tracers density. In the case of Kolmogorov turbulence. Rachmaninoff's law was in the case of chaotic flow. So the density spectral flux of tracers density in the case of chaotic flow is Rachmaninoff's law. Chaotic flow. For instance, at scales smaller than the Kolmogorov scale.
Vabandust, me ei näe praegu.
Thanks for reminding. I should have shared the screen, but I forgot to do it. Here you are. Here is what I wrote. And so spectral flux means that if you have some conserved quantity, you have some conserved quantity, which is transformed into smallest, like which can be fluctuations of which or fluctuations can vary to whatever structures, substructures, and so on can be are associated with, of which can be associated with certain scale, associated with different scales. Okay. Then in stationary case, you have you need to have a constant spectral flux. All right, and so examples which I gave you are listed above, but actually you can think of different possibilities as well. In a certain sense, there is sensitive to think in terms of population, you have also kind of spectral flux. Let us say the demographic situation in a country. Demographic situation in a country. You have people become older, and so they transfer from one age group to the other age group. So people are transformed during as time flows from one age group to the other. And now we have a constant spectral flux in that sense. So because if we neglect mortality for ages more than some typical maybe 60 years or so, then people don't disappear. We have conservation of people, and then we must have spectral constant flux if we neglect mortality at the age of smaller than 60 years, then in stationary state, population, total population remains constant. We have spectral flux of people. We have constant spectral flux of people. Spectral flux of people. So during each year, there is always the same number of people getting older than 60 years, than the number of people getting older than 50 years. Each year are as many people getting older than, okay, let's say 50 years, as many as there are people who get older than 10 years. Okay, and then from here you can from here we can derive stationary distribution. So each group needs to have an equal number of people in it. Each group, for instance, 50-year-old has the same number of people. Right. All right. Now, is the concept more or less clear right off? How you feel? Was this example helpful?
Yeah, this is clear so far.
Yeah. And now, well, this is quite trivial situation, but you can make have a little bit more complicated situations. I think there is now if you want to have some like more insight, like different examples, which in which case you have also constant spectral flux, then we can, for instance, we can now, yeah, how it depends how much time do we want to devote to it, but let me try. And if it gets too long, then we can stop at certain point. So I think it was called Takayasu's model of river or something like that, if I'm not wrong. Just from back from very long time, model of rivers, maybe. It was something like that. Imagine now a beach. A point in space, each point in space, or let's say in plane, a rocket, which moves randomly, like random walk. And now, for simplicity, just to keep it simple, let us assume that you can, the droplets can be only at discrete sites. Droplets can be at discrete sites. And during each time step, they move randomly by one x, say, by randomly by one step. And now we ask when, okay, assume that we add always more and more these small droplets. But then we ask what is the size distribution of the droplets at the end of the day. And then we can say that since we have a constant number of water, amount of water, we have a constant spectral constant. We need to have at the stationary distribution, at the constant a stationary distribution, site distribution of droplets. Droplets we need to have a constant spectral flux of water, which means that during a fixed time period, during one time step, as much water as there was with droplets, as much water as there before to droplets larger than certain a certain mass m. We can calculate droplets by mass, certain mass m. Sorry, now let me see. During one time step, the amount of water, which is transferred, which is transferred to droplets larger than a certain mass m, needs to be independent of m. And from here, from this condition, we can derive the size distribution of droplets. So basically, a little like try to reformulate this in a longer way. So we say that if let us say two droplets, which are both have mathematically smaller than m merge, then can form a droplet which has mass larger than m. So well, for instance, let us explain in more details. It takes if two droplets, one of mass m prime and another of mass m double prime merge with m prime smaller than m and m double prime smaller than m. And then so that the new mass m prime plus m prime plus m double prime is bigger than m, and then amount of then mass m prime plus m double prime was transferred to droplets larger than m. So that's what we mean by amount of water which is transferred. When I'm saying that the amount of water which is transferred to droplets larger than a certain mass m means that the total mass over all the mergers during this time period, such that the new mass is bigger than the old mass. Then the total mass is what we call the amount of water transferred.
So we're making like groups of mass.
Yes, but if we say that we size the distribution of droplets, that we characterize how many droplets have certain mass and distribution function. But if m prime was smaller than m, while m double prime was bigger than m, then the amount of mass transferred was a mass of water transferred was just m prime. Because m prime belongs to small droplets, but now the new droplets belongs to larger droplets, right? So the mass m prime was transferred to larger droplets, but mass m double prime was already bigger than m. It already belonged to larger droplets, so this was not transferred. And so we sum over all the transferred mass, and then we obtain the result. So basically, what we need to have so-called collision kernel. So we need to know how with which probabilities the droplets collide. What is the probability like in chemical reactions? We need to know the probability that the droplet of mass m prime collides with droplet of the mass m double prime, and then based on the stationarity condition and spectral flux constancy condition, we can derive the size distribution. Now, I'm not sure if and how much this was helpful, but actually this is something, this is, okay, I can write you a keyword here, and this is a small, something like that, I guess, small Hofke equation. Which is what describes this process. For instance, if you have droplets in cloud, and you need to and now so-called the collision kernel. Kernel is the probability that droplet of a size m prime collides with droplet m double prime to derive the spectral flux. From the condition constant spectral flux, we can obtain then the size distribution of droplets. All right. Now, how do you feel about it? Raida. Did this like expand or was helpful or just added more confusion?
I think I more or less understood. But yeah, if it described the spectral flux, then I like the demographic analogy more.
Yeah, surely. Demographic analogy is easy to understand, probably in that sense more useful. But why I added that droplet collision was just to show you that actually this spectral flux constants condition can be useful in very different situations. So just to you need to keep in mind when you're doing research or whatever that there is such a thing that which sometimes might play a role and can be helpful to derive something. And also another keyword that Smolkovsky equations is just you know that if you have a spectrum of sizes, in that case you describe it with Smolkovsky equations. So the droplet process is merger is described by what is called the Smolkovsky equation. So I think this was a Polish guy, Smolkovsky. Yeah.
Do we have constant spectral flux here? Because the size of the droplets also gets bigger.
Yeah, but we need to have always supply. So you have constant spectral flux if during each time moment you have always new droplets added. Because if you don't add, it dies out. They merge, and then you have only one large droplet at the end of the day. But if you have constantly new droplets, then you might have still ongoing large droplets, but maybe someone is taking out. If we speak about, for instance, clouds, then if droplets collide so much that droplet becomes very heavy, it just falls down and it goes out of the system.
Yeah, because the probability increases with mass.
Yes, that's exactly that kernel, the collision kernel. You're exactly right. That now the collision rate here depends on the droplet size. So the question is, what is the collision kernel? What is the probability that the droplet of mass m prime becomes collides and merges with droplet of size m double prime? That's what you need to know.
But then we don't have constant.
But you still have constant spectral flux because it's just the expression for the collision kernel defines what is the stationary spectrum. So suppose you have one situation where you get your collision kernel is independent of size m. So suppose that all the kernel droplets can merge only with a droplet of similar size. Let us play out such a scenario that we have a collision of two droplets happens when they come to the same site and have the same size. If they have different size, they are not allowed to collide. Suppose. Well, in reality, usually it's not the case, but it's just hypothetical. Just hypothetical. In that case, it's exactly the same as demographic situation. So you have like at each size of the droplets, the collision rate is, but it's not exactly the same because you see here, the transfer rate also depends how many droplets are there out. Because we can try to play it out. I'm not sure. Okay, suppose two droplets can collide only if they are at the same side maybe I need to continue to say the next page because I can see it's starting to going out of this.
So does constant spectral flux mean constant in time, not like that the amount of.
No, it's constant spectral flux. It's not in time. It is over the spectrum, regardless of droplet size.
The whole spectrum is constant.
It's a constant spectral flux means that the mass transfer rate of droplet of the water is independent of the droplet size M. Okay, well, let us play it out and then you might get better understanding. Let us try to play it out. So, with this hypothetical situations that what I was starting to write. Suppose two droplets can collide at the same site and same site and have the same size. But maybe the same size, but it's the same order of magnitude, like from M. More specifically, M prime divided by M double prime need to be between 0.5 and 2. Let us play sideshow. But if I say two different, they cannot collide, but if they are like have the same magnitude, order of magnitude, then they can collide. And then the collision point. Probability for two droplets to collide, droplets to merge, P. But now actually we don't need to have M prime and M double prime. Usually you need to have like M double prime and double prime, but now we can basically describe it with only one mass because the other has the same order of magnitude. So we can just keep this dependent on one of the masses. And then this is approximately equal. But because it's difficult to me to have here approximate sign, I can use that. Like approximately equal to now. You know the mass. Mass rule. Basically, the rate of chemical reaction is proportional to the product of the concentrations. Right, the same rule here. So the reaction rate. So P is basically the reaction rate, and this must be the concentration of the number of droplets of size M prime, multiplied by the concentration of droplets of M double prime. But they need to have the same order of magnitude, so it just goes to square. Right? Because M prime is approximately equal to M double prime, so the product of concentrations of droplet of size M prime and the droplets of size M double prime is approximately equal to just the concentration of concentrations. But let me, because now I started writing with a number, I write proportional to prop 2 M double prime. And so now we have condition that this is the collision curve. But this is not yet the spectral flux. Spectral flux is the mass transfer rate. Now, the spectral flux, the mass transfer rate, is now the reaction rate is prop 2. It's the reaction rate, which is M as a function of M prime squared. But now if two droplets of size M prime collide, the amount of water which is transferred to the droplet bigger than m prime is 2 m prime. So multiply it now by 2 m prime. But 2 is constant, so it is dropped to m prime and n squared. And now this must be constant. Okay, what we wanted to have, n, the spectrum. Hence, n drops to 1 divided to square root of m prime. All right. And here you are. We derive from the constant flux condition the spectrum of size distribution of droplets. Now, how are you? Is it more or less?
Still like wondering, like the constant part of the spectrum is then is the amount which moves between groups constant, or like what part is constant?
Constant, well, mass transfer rate. So how much water mass is transferred from droplets which are smaller than m prime to droplets which have mass larger than m prime. This is mass transfer rate, very tight. The mass transfer rate is how much water expressed as a mass is transferred from droplets smaller than m prime to droplets larger than m prime during a unit time. And now, because we expect to have stationary distribution, suppose we have the vector flux is not constant. It would mean that, so suppose, assuming the contrary, that assuming that the flux at, let me write it down here. So now, spectral flux, let us denote it F equal F, spectral flux F, spectral flux F. But this F is dependent of mass. Is proportional to is this is F, and this is proportional to this guy over here, and yeah. Suppose a contract. Suppose. That contrary means that F at m prime is, let us say, bigger the problem of having now a big its bigger sign at the moment. I cannot have now. Yeah, no, got it. Suppose the contrary f m prime is larger than f at m double prime. Nice words here. Okay. Because I have a US keyboard and Estonian layout, so that's what is in fact here. Suppose the contrary of f m prime is larger than f m double prime. Then the mass of droplets between m prime and m double prime and m double prime would change in time. if M prime, let us say if M prime is large M double prime, what does it mean? If M prime is large M double prime, then more water would go away to larger droplets than M prime, then there would be a droplet coming to droplets larger than M. Let me maybe draw here a figure on the screen. So here is a graph. Here is a droplet size M, and here is M. And now we have here certain distribution, and then here is M prime, and here is M double prime. And now we have, I said that the more flux is larger here than here. So more is coming in than is going out. So into this region here between M prime and M double prime, the amount of water would start increasing. The amount of water would start increasing. Okay, if we have if this and that. Okay.
Constant spectral flux.
So if the spectral flux is not constant, then the distribution would not be constant. But we expect that if we wait here long enough, then there would be stationary distribution. That's our expectation, that we achieve a stationary state. That if we supply all the time a new small droplets and big droplets drop out of the system, and then we expect that if we wait long enough, then we have a stationary distribution. And if we have this stationary distribution, then we must have constant spectral flux. All right, Railo. Is it now better with these droplets?
Yeah, I more or less understood.
So yes, it is very useful concept. So that's why I think it's useful to take a little time to try to just genuinely understand what it is. And once we understand what it is, then the Kolmogorov spectrum will become also very easy. Just you need to understand the key concept of spectrum, constant spectral flux, and that's it. If you understand it, then the rest is easy. All right. So, Railo, shall we close with this topic and go to questions of C?
I think we can move forward, yes.
Sorry?
We can move forward.
Yeah.
Yeah.
All right. And then there was Cherenkov radiation thing, I think what C asked.
Yes, specifically in like deep water.
Deep water, yeah.
Yeah, why doesn't it work there?
Sorry?
Yeah, why doesn't it work in like deep water, basically?
Yeah, it does work actually, but in a different
Yeah,
way.
but there was like an example of riding a bike to like some shallow puddles, and there are like deeper puddles, and in those deeper puddles it didn't work, you said.
So Cherenkov radiation is just that if you move faster than the speed of waves, then you generate waves. Do I need to write it here or just saying it enough? Radiation. Waves are generated when you move faster than waves. The Cherenkov, so-called Cherenkov radiation, Cherenkov resonance, Cherenkov resonance condition is a K. Now let me write it because with pencil is a K, which is wave vector multiplied by Just a moment. K dot V is equal to omega. V is the speed with which you move, K is the wave vector, and here is the dot product. So, which means that in terms of modulus, you have K times P times cosine alpha is omega, which means that the direction where you radiate waves, cosine alpha, direction of which wave goes cosine alpha is omega divided by K and B, but omega divided by K is the phase speed. So this is it denotes the phase speed as C phase divided by V. And cosine alpha needs to be cannot be larger than 1, so it must be smaller than equal to 1, which means that Cherenkov radiation becomes possible when your V is bigger equal than C phase. And so things are quite easy when you have no dispersion. No dispersion means that just you need to move faster than the waves, and you have Cherenkov razor resonance. And so there was examples that you drive on bikes through water, layer of water, and then you have shallow water waves which have constant speed, and then you have waves goes like one well-defined wavefront goes. The same happens when you have supersonic planes move. So with supersonic speed, you have so-called supersonic boom. Supersonic boom is exactly Cherenkov radiation. So supersonic boom, for instance, supersonic boom. But things are more difficult when you have strong dispersion, and things are more difficult when there is strong dispersion, like in deep water. Like for deep water waves. Because deep water waves, you have the relationship is what was it? Omega is omega is equal to square root of G times K. G times K, so the phase equal to omega divided by K equals square root of G divided by K. Okay, and then I see that there is strong dispersion of wave speed depends on the wavelength. And then while you can say that there are always some waves which are in resonance. Here, so when you have no dispersions, then you generate waves only when you move faster than the speed of sound. But now you have always, in principle, now you have now there are always waves in Cherenkov resonance. Resonance because whichever speed you take, there are always waves which move with the same speed as the waves. Short waves move faster, short waves move slower, long waves move faster. So for any speed, you will find a wave which moves at the same speed. All right. But now then there was actually quite a funny and not too difficult configuration to show where the waves actually like for deep water. Now I'm not sure how fluently I'm going to reproduce it here because it's a little bit like you need to think a little always before you're doing that. The magic angle under which you can see the deep water waves behind the boat.
You see it in the video.
Yeah, I think it was in the video, right? I don't need to reproduce it, probably. Do I? So we combine two conditions that in order to see now behind the boat, to see the waves somewhere nicely, and you need to have first these waves to be generated by Cherenkov resonance, because waves are generated when there is a Cherenkov resonance, and on the other hand, you need to have waves arriving there. If we speak about long distances, the wave energy needs to be there as well. So wave energy propagates with the growth speed. So we have thinking that we have two speeds. We have growth speed and phase speed. And in order to see waves behind the boat at certain point in space, the wave energy needs to have traveled over there with phase speed, with growth speed, and have at the same time a Cherenkov resonance condition. We might try to do it. I'm not sure. I can't eat house mostly close with that. But okay, let us suppose our boat is somewhere. Let us say boat is somewhere here right now, and but it came with certain speed, so that we consider now a wave which was generated back a certain amount of time, speed of the boat times time delay when what it was the wave back it was irradiated. And then we have the wave packet energy can travel in all directions, but with the growth speed. Wave energy is, let me draw now a red circle here. So it started at this point here. So we will look for waves which were generated back in time by amount t. So boat was here in that point of time. It was here, and the waves which were generated back then are now energy is on this circle over here. And this radius here is equal to c growth multiplied by t. Or the wave packets which now carry energy are on the red line over there. And but then they need to have, they were efficiently generated when they were in Cherenkov resonance. Means that that we need to have the direction under which they went need to be correspond to that Mach cone, so to say. So Cherenkov resonance means that the wavefront generated back there forms a triangle, right triangle. Now, but before I do drawing, let us see. We have phase speed is omega divided by k. Growth speed, v growth, is d omega over dk, is 1/2 of v phase. Oh, sorry, it's c. It's not supposed to be c. C growth. And then let me change it also c. C group is 1/2 C phase. So now our group speed is 2 times smaller than phase speed in the case of deep water waves, which means that the phase speed is 2 times bigger than group speed. Here is the group speed. Now I need to draw another circle which corresponds to phase speed. And now Cherenkov resonance means that we have we need to have if waves went that way, this need to be tangent, so to say. If this side here is C phase, and here is alpha, propagation direction alpha, then C V multiplied by cosine alpha must be equal to C phase. So this is a Cherenkov resonance condition. So which means that C phase B and V must form a right triangle of angle alpha, like geometry. And so here now we have that actually wave energy. Where are the waves which were generated back in time by about times t? Right now they are on the red circle, but a direction which corresponds to this alpha, so which means wave energy is right now here. Here is wave energy. And now, what is it exactly, and how do we how can we derive it? And now, basically, we would like to know that where this black dot here moves once we change the direction of angle alpha.
Like, what do you mean wave energies on the black dot?
Sorry?
What do you mean by wave energies on the black dot? Doesn't it radiate out symmetrically in a circle?
Once again, I am asking where are right now the these wave packets which were generated back in time by amount t. Where are they right now? And the answer is they are at the black dot, meaning that they could have gone in all directions on the red circle. But we need to keep in mind that they were generated due to Cherenkov resonance. So that this limits restricts their direction to correspond to Cherenkov resonance condition written over here. So their direction must be such that if I draw here another circle, then this line needs to be a tangent to this circle over there. Is it more or less clear? We have two conditions. One, it must be on the red circle, and second, the direction alpha must be right. And must be right. It means that if I draw 2 times bigger circle, tangent to this 2 times bigger circle, then from the tangent point drawn line corresponds to the resonance. So procedure: I draw one circle of radius CG, another circle of radius CP. And then from this point here, I draw a tangent to the blue line. And from the tangent point, I draw a line here, and intersection point here is where the wave package are right now. So those wave package which were generated back in time by amount of time t. And we would like to know what is at which direction. Basically, we would like to know this direction here. So at which direction, when we look from the boat, where are the waves? And now this becomes more or less like a geometric problem. Yeah, what you can do actually, you can Yeah, just from this triangle, I think you can calculate this angle over here. So it's a little different way of doing as compared to the lecture recording before, but you'll be able to obtain here also the angle at which you can see the wave values. So this is the same. Now, is it more or less what you wanted to hear, or you still have some more questions?
Well, I couldn't really get a concise answer on why exactly it doesn't work in deep water. Best I got out of is that the Cherenkov resonance condition is just not satisfied or something.
So what we don't have in the case of deep water, it is we don't have a sharp like shock wave generated. If you have the shallow water, you have something like a shock wave. You have wave which propagates. The boom, sonic boom is like a shock wave which propagates. This is because you don't have dispersion. There is a well-specified angle under which shock can propagate, and now in the case of deep water, the main reason, the reason why you don't have well-defined shock wave is that now you have dispersion. You have you have the resonance is possible for different waves, and if in the case of no dispersion, resonance wave propagated in only one direction. Now, in the case of deep water waves, because the phase speed is not constant, it depends on wavelength. For any direction propagation angle alpha, you have different wave speed and different wavelengths, which generates which are generated in terms of Cherenkov radiation.
Okay, yeah, that makes sense.
If it was concise enough, but
yeah, that was good. Yeah, that's what I wanted to. Yeah, thank you.
Yeah, because you have different speeds, different wavelengths. So Cherenkov radiation is no longer in a well-specified direction, but each wavelength has different direction where it goes Cherenkov radiation. No well-defined single direction. And because previously, like all the energy which was generated was focused into one direction. And now you have a multitude of directions. So in general, you can say that actually there is also no shock wave, but rather just more peaceful, so to say, wave packages which propagate now.
Didn't you have enough energy, like an astronomical amount of energy, so that in all directions?
No, as the amount actually, this is what is important for by wave drag is that what Kaspar asked about amount of available energy. Available energy has much to give. In order to have a boat moving, you need to supply energy to generate waves, because boat needs to generate waves if it is in Cherenkov resonance. It needs to generate waves, but you need to give energy to generate waves, because waves carry away energy. So it means that you need to supply energy to the boat, or if you don't supply, the boat will slow down. So this links us to wave drag, which means that as long as you have Cherenkov radiation, in addition to the previously known types of drag, like viscous drag, turbulent drag, now you have also wave drag. This is another totally new type of drag, which is very important, and it can easily become the dominant component of the drag. If you take a small boat and try to accelerate, then at certain point, you basically it will become impossible to move faster, because if you try to increase the thrust of the motor, then just what you do is you generate more intense waves, and speed will increase only negligibly, because wave drag grows proportional to the cube of speed. Viscous drag grows proportional to speed. Turbulent drag grows proportional to square speed, but wave drag grows proportional to the cube of speed. And yes, this becomes the question of how to design boats. So boats, if you want to have fast boats, they need to be constructed so that Cherenkov radiation is somehow suppressed. Whether a very good shape like kayaks, for instance, very narrow, long shape. So why do we need to have a long shape of the boat? It is because you can suppress, by shape of the boat, you can suppress those waves which are shorter than this size of the boat. But generally, waves are like all those the protrusions and whatever on the boat, and they generate the waves which have the same order of magnitude than the size of these structures. If you take a long boat, it will not generate waves which are shorter than itself, but they necessarily generate waves which have the same length as the boat itself. So, because of that, kayaks need to be very long so as to not generate waves, so that not to have Cherenkov radiation with those waves which it will generate. It will not generate very short waves, shorter than itself. And so critical speed basically can be estimated. Critical speed is the speed by which you start intensely generating waves and having significant wave drag is the speed at which the waves corresponding to the length of the boat are in Cherenkov radiation. I think that's so. Everything actually was also in the lecture recording, so that's I was not writing on the screen, but. And this you can actually there are possibilities like to having active shape design like boat those, and you just to try to actively change the shape of the walls of the boat so as to suppress the would be formed to be waves behind the boat. This is one possible direction. So this is a great challenge for boat design to suppress waves as much as possible. Yeah. See, you can now?
Yes, can you repeat one thing? You said that wave drag grows proportionally to what speed?
Q. Wave drag is Q as a Q. So also, this means that if you have supersonic flight, then it goes also the same way. So at Mach number larger than 1, which supersonic speeds, so the drag also starts to become dominated by wave drag, and also grows as a speed cube.
So during the radiation, let's say reactors, the blue light, that's a wavefront actually.
Sorry, what again?
The blue light we see in like reactors, the Cherenkov radiation,
Yeah.
right? That light we see is actually a wavefront caused by faster particles.
Yeah, so particles which come towards you. Now, if in the medium you have a phase speed smaller than the speed of light, so relativistically it's possible for particles to move faster than the wave speed in the medium, So they will be assuming there is no dispersion, then it's the same. It is the same as in the Mach curve. So we have a certain direction at which they are in resonance, and this is where it is generated. So
it's a problem,
that's making drawing here. So here is your particle moves, and now the same way as you draw with the Mach curve. So here is like something like that. Okay, so as here, if wave goes, sorry, now it's perpendicular, so it goes like that. So here, if wavefront is like that, and if phase speed is directed that way, now if that phase growth speed is c equal to n, and now here and the Cherenkov radiation condition is v grow multiplied by cosine alpha is the speed of the particle, and so we have c divided by n cosine alpha equals to v. But if we have like ultra-relativistic particles, this can be around of c, very fast particles move like almost with the speed of light. No, something was wrong. Yeah, it's the other way around. It's the other way around. Cherenkov radiation condition is v cosine alpha is v group, and so v multiplied by cosine alpha is v group, and this is equals to c divided by n, but v itself is approximately equal to c, so c cancels out, cosine alpha is then approximately equal to 1 divided by n. So you can see under which angle you will see that the blue light.
And then it's
Sorry?
n is what?
N is coefficient of refraction.
Oh,
Well, it's not necessarily blue light, any light, because as long as you have no dispersion, so and it's just the same for those waves. And so you can see that if you have n dependent of the wavelengths, so you can have different wavelengths, is highly different angles under which you can see.
the dispersion of the wave, you mean?
A dispersion means in that phase speed depends on wavelengths. Dispersion means wavelength wave speed depends on the wavelengths. This is what means dispersion. So for sound waves, there is almost no dispersion. Whichever frequency of sound you take, it propagates with the same speed. For speed for light in vacuum, there is also no dispersion because it is always c. In the medium, you might have a quite significant dispersion, and this can from time to time become quite troublesome if you take a good photographic lens. Then dispersion means that you optimize it for a certain wavelength, and then it is different for another wavelength, and then you have also purple fringing and things like that. And so then you pay a lot of efforts to compensate for the dispersion by combining like different tricks, like combining different glasses with different dispersion relationship. Dispersion relationship is how depends omega on K. Dispersion, nothing like dispersion relationship. Omega as a function of K. Omega equals omega plus function of K. No dispersion. Is omega is speed of sound times K, and Cs is constant. Cs is constant. This is no dispersion. But if you have dispersion, then you characterize with the dispersion relationship omega as a function of K. And this can be of anything, basically. If you read deep water waves, it was square root, right? Square root of K was dispersion relation.
And
Deep water. And 3 times K. Okay. This is dispersion relation. Shallow water, we have no dispersion. Temperature is, you need to have something moving.
yeah, wave
Something
of
moving.
a Kelvin wave.
Kelvin waves, yeah, you can have
Another wave of temperature, or like another front of temperature, or like what would you get from that? Like, what would be the Cherenkov radiation version of a Kelvin wave? What would it radiate?
as long as you have phase solutions. Right, yeah, there is actually, I think it was also in the lecture recordings, but there was in sometimes in polar regions, there are so slow waters, or how say call it, but you can have situation that you have a ship somewhat over there in polar regions. And then say pulls the engine at full thrust, and they move just maybe 5 kilometers per hour, so very slowly. And then why is that? It is because you have a salinity. You have here is water surface. Here you have fresh water, which because you have ice is melting. And then you have here fresh water. That's from melted ice. And now down there, you have ocean water. Ocean water. Water with high salinity. Now this is more has more higher density. So here we have row 1, here you have row 2, and row 1 minus row 2 is more. And now what was now it's more or less the same as we had in the case of Rayleigh-Taylor instability. Since that was unstable, but now it depends which is bigger, row 1 or row 2. So if row 1 is bigger than row 2, then we would have a Rayleigh-Taylor instability. But now we have the other way around, it's stable. And then we have something like that. This is phase now is something like that. We phase, but now we have waves. Actually, we have you can have actually. Depending on the depth of row 1, but basically the freshwater layer can be very small. And then you have something like that. The steps here is age, then you have something like yeah, if depth would be bigger, then it would be easier to write down. So then it would be the phase would be square root of what you used to have g times g divided by k, but now we have a ratio of densities rho 1, something like rho 1 plus rho 2 divided by rho 1 minus rho 2. So that if rho 1 minus it's other way around. The dominate has minus and has plus. Minus. Here you have plus.
Not sure if the Zoom is recording, but it's frozen.
Okay. Let me see. Zoom is recording, but this right now we have the screen again. Yeah. So rho 1 minus rho 2 divided by rho 1 plus rho 2. So it means that it becomes very slow. Okay, it becomes very slow. And if you previously, you remember that the condition is that wave size gives you the waves which are generated. And so those must not be as the Cherenkov resonance condition. So basically, you cannot generate, you cannot move faster than the waves which are same length as those. So critical speed. So but you cannot move square root of g divided by k. It is the phase speed voice k approximately equal to 1 divided by the length of the ship. Wave vector corresponding to the length of the ship. So you cannot generate waves which are, we always generate waves which are longer than the ship, which move faster than those with a critical length. So you generate waves which you generate. Waves, a voice. K larger or order, like sorry, it's other way, which are longer than, which means that k is smaller than 1 divided by n. Okay, correct? Wavelengths. If the wavelengths have the same order of magnitude as the shift lengths, then k equals 1 divided by n, right? And then I'm saying that you will generate always waves which are longer than the shift. And you will not generate waves which are shorter than it. You can design the shape of the boat so that you will not generate. So you always necessarily generate waves which are longer than the shift length, which means that wavelength of k is smaller than 1 divided by n. And then they move with speeds which are larger, which are larger than the wave frequency. So you generate waves, voice, v, but v is a decreasing function of k. If you have k is smaller than 1 divided by n, and v is bigger than order of square root of g times n. Okay. I substitute just this I put into here, right? And so you always generate waves which are larger than g divided g times square root of g times n. And now, in order not to have Cherenkov radiation, means that you cannot move faster than square root of g. Wave drags will not let you move faster than square root of g. Okay, that's what we normally have. That's why you make long ships. To move fast, you need to have a long ship. Okay.
So you have two ships, same power, but one is longer, the longer one can
That's
actually.
correct, much faster. That's why Vikings had it. Like the evolution of Vikings was having long ships. And then, but now look, if it's a slow waters, what we need to do is we need to substitute. We have this now. So instead of G, we substitute G multiplied by rho 1 minus rho 2 divided by rho 1 plus rho 2. So now this goes to square root of G and rho 1 minus rho 2 divided by rho 1 plus rho 2. But this guy here is now very small because density difference is small. So just as boat tries to move faster, puts the engines at full thrust. The only thing it will do is it will generate huge invisible waves. Invisible waves because these are waves between the layer of fresh and saline water. You won't see it because it's down there. They look the same. Fresh water and saline water, they have such very close. You won't see the waves, but they are generated. If I move faster, you will not move faster because you generate the waves.
Do the waves get down there? How do the waves get down there? Like down the
Yeah, if it's very deep, then it will not generate. So actually,
okay.
yeah, it's like it works if the yeah. All right. What else? See. Any else? So was it quite more clear?
Yeah, this was very good. Yeah.
And yeah, like making all the summary of important points. So the important point here is that the wave flag. The wave flag is that, which means that both it doesn't make sense to try moving faster than the design speed. Like you can perhaps move slightly faster, but actually you start spending much more fuel to move faster. So
But why do speedboats like race up the water?
yeah, that's yeah, speedboats. So now different ways of actually combat this wave flag. One is so-called underwater wings. Yeah. So in that case, what you make is just the object itself, which you make it small. The boat is big, and well, it's big. It affects a lot of water around it, and so the base becomes also respected. So now, if you take speedboat weighs underwater wings, then now what's the difference between normal wings and underwater wings? The difference is in the density of medium. So here has density of 1 kilogram per cubic meter. Water is 1,000 times bigger than it. Now wings, why it shows that you compensate the weight by dynamic pressure. Rho is square times 0. Should I write things or is it better if I write? Rho here around 1.3 kilograms per meter. Rho water 1,000 cubic meter. Now M times G is compensated by dynamic pressure surface here and multiplied by rho v squared divided by 2. Now, this means that with by the same speed, actually surface area can become 1,000 times smaller. So it means that your underwater wings actually are very small. Not the speed the wings you use now. So they are small things underwater. They have small, like something like that maybe. Here is your boat, big boat. No, it's like that's a boat. Here is the boat, and here is your maybe here some wings here. Here are some more wings over here to make it stable, and then these are small boat speed. So just because the cross-sectional area here is very because small, so even though they will generate, they are like in Cherenkov resonance, but its size is so small that it's still very rapid. It becomes also not that big now, and because of that, we can move much faster. This is one possibility to have a speedboat. And if you have another thing is possibility of speedboats, if you don't have underwater wings, then you can just have some like if you move fast enough, then dynamic pressure will rise. So if you move slow, then your boat sinks into water. Like that. Okay. Now, if you move very fast, dynamic pressure, this guy over here will rise it up. And now it goes like that. Okay, now it will rise and it just a little bit. Because now, okay. And now also the cross-sectional area, which basically interacts, becomes also much smaller. And this also in the same way will reduce the drag, including the wave.
The length is the length of the ship.
Yeah, even if you have so in those cases you can have like violation to a certain degree. What I said before, it still remains valid. Even though your wave lag is reduced by either the fact that you are using underwater wings or just the dynamic pressure will rise about, so that because of that the wave lag becomes smaller. It becomes smaller, but it will not go away. So regardless, still you will have wave lag, and still the size of the ship will become also important.
There is another component to wave lag.
It is still the same wave lag, but the wave lag has two components. One is a wave lag F is certain factor K and BQ. Basically, what you do is you reduce the K value. Both effects reduce K. This underwater wings more, and this glycerin investing or something, how we call it. This reduce less, but both decrease K. BQ remains. But still, it makes it possible to move significantly faster than otherwise.
What is the second? What is the second part of F? Probably it's two parts.
Oh, one is K and other BQ.
But what?
So VQ is always there, but you can play a little with K. And that's basically all the boat design is playing with K, reaching up as small as possible K.
But we just saw that K is dependent on one the white variable.
Yeah, K. Okay, all right. We can also say that K is certain. And now I want to denounce like kappa. Kappa divided by. Okay, kappa. No, it's just not good. That's not good. Something like now, if we figure out how it might depend on the so K depends on the length of the ship. It is not that So this relationship if you really exaggerate the waves a lot, but you will not. That's what I'm trying to figure out how to write it to bring to the place that the ship lacks L. Maybe in such a way. Let me write the difference way. The cliff is a certain prefactor k, and then those v divided by square root of a gl and the power of q. Something like that, maybe.
I think I understood why raising the boat out, like even if you reduce L, you're probably reducing like drag from viscosity, I guess, because more of your boat is out of the water. So you're not reducing weight drag, you're actually increasing weight there a bit, but at the same time you're reducing other drags.
Well, yeah, of course, you don't need to forget other drag as well. But still, the most important thing is always wave drag for boats. Almost, unless you don't know relatively slow. But I think this formula is more or less okay. So if you look at here, you can you have cubic dependence, but if you make a big longer, then the cubic dependence will just be reduced. So basically, if you reduce the prefactor between the proportionality factor between force and the speed cube itself is a decreasing function of L. The longer L you take, the smaller K becomes. Something like that. But this is not the whole story, but again, if you take like a ship which can rise if you go very fast, so like a small speedboats, usually like that. If you move at slow speed, it sinks into water to certain depth. If you move fast, it's suddenly it rises up. And then in those cases, if you plot force, the drag force and the function of speed, it can even have like opposite dependence. So F and V, maybe it starts growing. Yeah, it goes up like that, and then it maybe it goes up, and then goes up again. At this point, it still sinks into water, and now dynamic pressure will ride it up. So the prefactor K goes down, drag is decreased, and then again, once the speed increase speed again, then the drag force becomes big again. Something like that.
You said K goes down.
Yeah, okay. That's the initial formulation of F. I have kappa goes down. F equals kappa multiplied by L cube. V cube. The kappa goes down. Okay, goes down.
It rises out of the water, so
Okay, L goes down. Sorry.
it rises out of the water, so L goes down, but
No, not L basically doesn't change much. If you have both like that, the length is doesn't change much. Shape of a boat is like okay,
right.
This length will not change much.
some of the speedboats I've seen have like an extreme change, like at least 2 times shorter on the hull than.
Oh yeah, this is like actually it's because the oncoming water just raises the top above like yeah, I know what you mean, but yeah, then the decrease of K compensates for the decrease of L. Because if it goes move very fast, the faster you move, the higher it rises, in the water is small as the contact area, but also the smaller cross section. So what is also plays a role is the cross section, how deep it is immersed. How deep it is immersed. So basically, prefecture K depends how deep it is immersed. If you move faster, it becomes less immersed.
So K is
So I'm saying that K becomes smaller because it is less deeply immersed.
so K is also dependent on depth and
Yep.
length.
Correct. Now, anything else we can't discuss? Team, are you happy? Team, are you still there?
Sorry. Yeah, sorry, I didn't hear you.
Everything fine with you?
Yeah, okay.
So if there are no more questions for this lecture, I can also start 15 minutes earlier. Usually you go a little over, but I think from time to time it's okay also to stop earlier. So if you don't have any more questions, then that's what I learned.
I had a question about K, how to understand K better, but maybe this is not necessary to be recorded.
Okay, I can stop recording and then I can discuss over to Estonian and maybe also a little, if you are interested in boats, then we can. First, I need to stop share this. And stop recording.